Right. So I can start now. I'm going to talk about the research in particle physics. And since this is done mainly at CERN, the European Particle Physics Laboratory, which is located at the border in Geneva, at the border between CERN and France. Here in this picture, you see the Geneva airport below, and on top you see the mountains, and the dashed line is the border between France and Switzerland, and the circle is the accelerator. So how do I go to the next slide? You have to do it, Maria Luisa. Okay. So CERN, you can see the website on top, is more than 65 years old. It was just started after the Second World War. And it has 23 member countries, 14,000 researchers who come from all 5 continents. They are not really the ones, the CERN personnel. The CERN personnel is sort of maybe 10% of that number, but they are visitors from 80 universities, 800 universities and research centers. And the reason is that CERN has the unique facilities, the accelerators and the experiments. Hand in hand with the research goes also the high-tech technology, the cutting-edge technology, and at the same time, it has a lot of educational programs from high school to doctoral students and researchers. Next slide, please. So now the question has been, how do we search from the big to the small? How do we see it? Can you click, please? So we go from the atom, if you want, which we can call it 1, to the quarks, which we can call it 1 over 100 millions, and the electrons, which are much, much smaller. Next. So to do that, from the big, we go to telescopes, we go to satellites, and going down, we go to the human eye, to microscopes, to electron microscopes, and finally to go to the smaller and smaller dimensions. To investigate them, we need the accelerator, and CERN provides them. Can you click? Okay. Again, fine. Next one. So, in order to look at something, we need to have, first of all, the right probe and the right resolution. So on the left, you see something that is hidden behind the picture. If you use a basketball ball, you don't really see anything. If you use a tennis ball, you start seeing something. And finally, if you use a golf ball, you see the whole object hidden behind. So the lesson learned is that you need, please click, you need the right wavelength to see, and see in quotes, the different sizes on the objects which were shown above. Next one, please. So this is the picture we have and we had about the nature and the forces. On the left-hand side, you see the particles that constitute the matter. They are the quarks on top, yellow, and the leptons below green. You can see they are both divided in three families, going in masses going from left to the other, from smaller to larger mass. The particles that we have experienced in everyday world are the UD quarks, which are the constituents of the nucleus, the electrons, and the muons, which are the constituents of the cosmic rays. Now in purple, you see the carrier of the forces. The elementary particles interact between themselves using the carrier of the forces. Here we have the three forces, the strong, the electromagnetic, and the weak. We are not talking about the gravity because it's totally different. The strange thing that was known for many years is that while the strong and the electromagnetic force have carriers that have zero mass, the weak force has carrier, which was discovered about 30 years ago, carriers, let's call it because there are three, which are very heavy, like 100 times the mass of the proton. So the question was why? And the answer was given by theories, and the strongest theory was the so-called brute Engler-Higgs mechanism, which predicted the difference in masses, but also predicted the existence of the Higgs boson. So somehow the Higgs boson had to be discovered. And up to about 10 years ago, we had not discovered it. CERN had to construct a dedicated accelerator to have enough energy to create it, and dedicated experiments to detect it. And the choice was given to be protons colliding with each other with extremely high energies, like 7,000 times the energy, the equivalent energy of the mass of the proton. And this way, the Higgs boson, if it existed, it had to be produced. Next slide, you see a schematic of the accelerator. This is called Large Hadron Collider, LHC. It's housed in a 23-kilometer circumference tunnel that was existing before at CERN, and it's underground, as you see here. Below the surface, there are points, interaction points, we call them, where the beams collide, and there they are housed the large experiments which detect the products of the collisions. Next slide. During the construction of the LHC, the most challenging component was the construction of the dipole magnets. These were very, very strong magnets constructed in 3 places around the world, about 1,200 magnets. And the challenging thing was that the current that was circulating in the superconducting coils that consisted of the magnet was 12,000 amperes. Of course, the magnets are cooled because they have superconducting magnets, and they are almost at absolute zero, 2 degrees above absolute zero. Next one. So what happens in the LHC? There are beams circulating in opposite directions. You see the blue and the red, and they collide. Actually, they are packets of protons that collide with each other. The collisions happen around a billion times per second. And out of this, only very, very rarely, some interesting particles come out of the energy which share, let's call it, the energy of the collision. Up to now, we have discovered the Higgs, and maybe in the future, some more particles will be discovered. Next one. So, in order to detect the collisions, which happen at those interaction points, 4 experiments were built around them. The top 2 are the so-called general purpose detectors, very large detectors that could detect everything. And the 2 below are more dedicated experiments. Now I will go to talk a little bit about the top left detector, which is called Atlas, and this is the experiment or detector, if you want, where I participate for a number of years. And in general, Greece has contributed also to the construction of the experiment. Next one. So Atlas is located across the entrance of CERN at a specially constructed pit, underground, let's say, cavern, which has a length of 55 meters, 32 width, and 35 height. And as you see, Atlas occupies almost all the cavern. It has been installed in 2008, and it was built underground from these large tunnels using the components like a little bit like we built a ship in a bottle. Next one. So I don't know if you see the person below, but this gives you about the size of the detector. It's like a 9-story building. Now the different colors here indicate different parts of the detector called subdetectors, which they do different functions, measure different particles, or identify different particles. Next one. Here just a schematic showing you below is the place where the interactions happen, and you see the different particles as they propagate in a slice of the detectors. Some stop in the green detector, some stop in the brown detector, and some go through and stop on the top detectors, which are called muon spectrometers, because the muons stop there. And that's where the Greek contribution to the experiment was given. We have constructed about 10% of the muon spectrometer in Greece. If you see the dotted line on the right are tracks of neutrinos. The neutrinos cross the detector without leaving any trace. Next one. Okay, this gives you the complexity of what we have to face. This collision happened very fast. They could be not only one, but several proton collisions at the same time. Hundreds of tracks come out of the collisions. We have to reconstruct those tracks by software and also pick up the most interesting one. As you see, the 2 yellow tracks on the left side of the picture. Next slide. So this is a 3-dimensional picture of the product of a collision. It happens to be a Higgs particle. This is an event, that's what we call the product of the collision, collected in 2011. And this Higgs particle decays very fast because it's heavy in 4 muons. So you see the 4 blue tracks giving signs to the detector. Now we have, of course, hundreds. We have detected hundreds of Higgs particles. And since more than 10 years ago, we have developed a special software together with Stelios Bourakis at the University of Athens, which is called Ipatia, and you can study these pictures of event collisions and analyze them. And this you can provide to your students as well. Some of the Greek colleagues who are present now at the webinar have been using this software, have brought their students to the University of Athens, or we have gone to their high schools and we have used this dedicated software, which is part of 2 of our demonstrators and are already translated in several languages, between them are Greek, to use them in their class. Next one is the discovery of the Higgs boson. So you see how slowly, starting in 2010, we collected data. In the beginning, we saw nothing, and then slowly a peak, a concentration of events developed around 125 GeV. This was announced as the discovery of the Higgs boson in 2012. This is one of the ways the Higgs boson decays. The next picture shows another way, well, shows the same thing again. Let's go to the next one. Okay, this is a much harder decay of the Higgs boson because it's buried under a lot of background. But as you see a small bump developing at the same mass, 125 GeV. Next one. So the Higgs boson was there. The statistical analysis showed that it was above the expectation of the background, and it was located at 125 GeV. Next one. So the Higgs boson discovery was announced 8 years ago, the 4th of July, at CERN and at the big conference in Australia at the same time. Next one. And 1.5 years later, Higgs and Engeler received the Nobel Prize in Physics. Brute, unfortunately, had died in between. Next one. So we had discovered the Higgs boson. So we had answered one of the questions of the standard model, which I referred to in the beginning. Why, for example, the carriers had such a mass, why the particles had such a mass. But there are a lot of unanswered questions, and that's why the high energy research goes on. I had listed here some examples, like what is the dark mass and energy? Why do we have more matter than matter? I have not talked at all about gravity because we cannot connect it to the standard model. Why are the quarks and leptons elementary, and why they are listed? They could be classified in 3 families. Okay, I'm almost finished. I just want to give you now, I gave you an overview of the research done, but I want to show you some slides about the applications, the technology applications done at CERN. For example, medical applications, MRI, PET, hadron therapy, all this came from CERN. Next one, some technological application like the touch screen was developed at CERN. Superconductivity, of course, got a big push constructing the magnets. Next one, everybody knows that the World Wide Web was invented at CERN. And finally, the most recent one is the grid, the technology of the computing grid. Thank you very much.
Thank you very much. Professor Kourkoumelis, do we have any questions? All the presentations will be shared to you by the end of the day. You will receive them, the link to them, so you will have the time and the space to look at them at your pace. If we don't have any questions,